So now the question is, what can I do to these matrix systems to get them reduced? And there are three things you can do, and only three. All right, so you have to only work with these three things. So one is called replacement. You replace one row by the sum of itself and the multiple of another row. So you can add a multiple of one row to another. So we did this a lot, right? So this would be like replace row 1 with row 1 minus 3 row 2, right? So that would be a replacement multiple. And you can do this because you can do this with regular linear equations, right? We stack those linear equations up, make a little addition problem and add them together. So if we can do that, then we can do this with our rows when we're just dealing with the coefficients, okay? We can interchange two rows. We did that before. We could say switch row 2 and row 3. We just change the order. And why can we do that? Because we can do that with equations, right? The equations in the system, the order that they come in doesn't matter. So we can switch the orders around. We're going to have the same solutions. And we can scale. We can multiply all entries in a row by a non-zero constant. So we did something like this. You can replace row 3 with a negative 1/6 row 3. We just multiplied that row by a constant. And this is how we also use this to do division, right? Instead of dividing by negative 6, we multiply by negative 1/6. So you get division baked into this. And we can do this because if you multiply the same constant on both sides of an equation, the equation is still true and your solutions are still the same, right? So all these things are things you can do to equations and you maintain the solutions, right? You don't mess up the solutions. So really, as long as you do these operations and you do them correctly, you don't make mistakes, you're not going to mess up the solutions. Now you can get into kind of loops where you don't make it any closer to finding your solution, but there's always a way to come back. The only thing you really shouldn't do is don't multiply a row by 0. And that will just zero out your row, and you're going to lose information that way. Okay, so you don't want to do that. We say two matrices are row equivalent if there is a sequence of elementary row operations that transforms one matrix into another. So if you do one of these operations, we say that the matrices are row equivalent. They're not equal though, right? So they're not the same matrices. So if we go back, this matrix is not the same as this matrix. Something has changed. The rows are switched. So they're not equal. So you can't write an equal sign, okay? But we have a symbol for row equivalence. It's the tilde. So you kind of make a tilde sign if you want to write these two are row equivalent. Then you can use tildes, but you can't use equal signs because they're not the same matrices. Okay. If augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set. So if you do these row operations and you do them correctly, and you get row equivalent matrix, then the solutions are going to be the same. So this system here, right, which I wrote down with variables, that system has the same solutions as the very first system, right, which is how we found our solution, right? We simplified the system, okay, but we didn't mess up the solutions.